over. Hang on. Okay, somewhere hopefully down here below the exit button, I'll put the inset of what's going on the POCASA board itself. So first I got it up and running. I hit the ID. I got POCASA revision 0.7 because everybody likes point this and point that. So quick transfer rate check. Transferring 18,000 give or take bytes per second, 180,000 BPS, 180,000 baud should show up, right? 181,800 baud coming from the PC to the PIC. I'm coming back the other way. And this is a fair amount slower. I know why. I got to fix it. No big deal. Let that finish cooking because can't do anything else till it's done cooking. See, it's showing 8,300 bytes a second there, 8,300-ish bytes a second. Okay, 83,780 bytes per second, which comes out to be 837,000, no, 83,780 baud, BPS, whatnot. Okay, I'm going to turn this thing on. I got to set a few settings that I don't have hard set in the code yet, just so that I know these settings work. Basically, these here are the gains and the offsets for the X and Y op amps leading to the ADC. This is for the direct digital synthesis. The gain and the offset. This is to set the voltage on the coming out of the DDS. This is to set the offset, whether it's centered on 0, a little above, a little below, all the way above the 0 line, all the way below. This is a 4-quadrant DDS generator. Does positive, negative, both ways. Let's make a frequency here, 60 hertz. And you know what? I should fire up the oscope just so I can show that it is doing something here. Plug this in. Then I'll have to swing the camera around. But I got to give it a ground here. Make sure not to short it out. Okay, there we go. There's the DDS. Okay, so you can see I got 60 hertz here. I'm gonna pick up the webcam and just show it on the scope here because the scope capture software is garbage. Hopefully we can see that. Okay, you got 60 hertz. And now I'm going to dial it up a ways. It says 89,000 hertz there. Right there, it says 89.467 kilohertz. There's our wave. Okay, great. Now I'm going to dial it back down to 60 hertz. There we go. 59.99 hertz. There's our wave. And if you don't believe, there's 59.99. Now I'm going to turn the frequency up manually here. God, I wish I could hold this thing steady, but I can't. Don't worry about it. Don't care. Okay, so now I'm going to dial up the frequency. I think. Yeah. Okay, it is going up. Let's make this a little bit quicker. Nope. There we go. You can see my frequency's going up there, 80 hertz, 90. Let's crank it up fairly quick here. There's 217 hertz. Shows 217 on the screen. I'm going to take it back down to 60. 60 is a good round number to work with. $671 is what I want. Okay, that just shows that I'm actually throwing stuff out there. Okay, 2 pins over here. Now I'm going to go ahead and get a sample in. Open is the horizontal line and shorted is the vertical line. So let's go ahead and get 1,024 samples and hopefully this works first try. There it is. Oh, I forgot to turn on my outputs. There we go. Let's clear the screen. Draw a little bit of a grid here. I don't know if you can see it or not, but there's the center line. Okay, there's my open. I'm going to take the red. I don't know if you can see this or not, but I'm going to take the red, and I'm going to short this out. In fact, I'm going to put this on continuous. I'm going to clear the screen and put it on continuous real quick. When I short this out, it'll go to a vertical line. Okay. Whoops. Forgot I was going to go to continuous. Okay, let's go to continuous. There's my continuous. There's my horizontal line showing it's open. And I'm going to put these on here. And there it's showing shorted. Straight up and down. Let's clear that off. Here you go, showing straight up and down. Now, that's open, that's short, that's fine and dandy. But what we really want to see is components. So here I got a diode, standard, let's see if we can zoom in there far enough, maybe not. Standard 1N4148, no. No, it's a 1N4004 diode. So, plugging this in, and what you should see is a chair. It's clear, it'll show open, and it'll go, and there's your chair. Over on this side is on the negative side. This is where it's all the voltage going through it is negative, so it's not conducting anything. And as the voltage goes positive, the current flowing through it gets higher and higher. Here you go. So if we turn the diode around, we'll show a chair going the other way. I just turned the diode around. There's a chair going the other way because, let me clear it and redraw the grid. On the positive, the current going through a positive, because the diode's backwards, it's not conducting anything. Goes a little more negative, all of a sudden starts conducting. There's your diode. Oh, let's show one more thing, a couple more things here. I'm just going to set this down so I can click easier. Okay, let's clear that off. Up here I can change the resistance. Up here, the source resistance. So we change the source resistance to 8 different settings. And you see the basic picture stays the same. Although the offset as far as how negative the voltage has got to go changes a little bit. But the picture still stays the same. It's a diode. Unmistakably a diode. We'll set it back here to the lowest resistance. Clear the screen quick. A diode. And frequency doesn't matter. Now in this case, there's a little bit of capacitance going on here, so you might see a little bit of a circle kick in. But I cranked it up to 89 kilohertz there, 89.5 kilohertz. There's a little bit of a circle, and well, that's all circle now because I don't have enough voltage left over to drive anything. So we crank up the voltage. That's still a diode, because it's got the chair going on down here, but now I'm reading a whole lot of capacitance going on here because, again, it's my design here and it's got to be fixed and whatnot. But this thing wasn't designed to run at 89 kilohertz. So let's just run it up here to 4.5 kilohertz. That's good. That's a good round number. Oh, too much gain. A lot of distortion there once you get too much gain. There you still see a little bit of capacitance right up in here, but not nearly as much. And that might be a function of the diode too, because there is junction capacitance in there too, PN junction capacitance. So, all right, wind this down. Eventually, we're not going to see any of that capacitance. Now I'm going to switch over to a, what do I got here? What is it? Here it is. Is that it? It's a 100 ohm resistor. Okay, 100 ohm resistor. Don't think it really matters if see it or not. Resistor doesn't care about voltage. The lower your voltage, the smaller your signal. The higher your voltage, the larger the signal. And the little tweaks at the end there is distortion, because I got too much voltage going on here. It's clipping. So let's just try that then. 150. I still got to characterize this thing all kinds of different ways, but okay. Source resistance, however, does matter. Right now we're on the lowest resistance here. A perfect 45-degree angle would mean that the source resistance is equal to the resistance across this. So once I get up to, I think it's 2, setting number 2 should be pretty much a 45-degree angle. Yeah. There's your 45-degree angle. So if I go to lower resistance, the board resistance is lower than this. Therefore, it's a flatter line. The board is the device being tested is more open than the board. Therefore, the line is flatter. Now, if I go to a higher source resistance, let's just go ahead and go all the way up to 8. Now, let's bring it back down to my 4th resistor here. 4th resistor is 750 ohms, give or take. My tested resistance is more shorted, more vertical than the board's resistance. So you can tell what's going on there. Now I'm going to leave that same setting up there, and I'm going to pull this 100 ohm resistor out and put a this is a 1K ohm resistor. Watch where that vertical line is. See? Now it's gone flatter because this resistance is more open, higher resistance than this resistance is. So it's flatter. And again, frequency doesn't matter with the resistance. That's a little too high. We'll just go back there to 89 kilohertz. There you go. That's the sign. Go back down to 60 hertz. Now I'm going to throw a capacitor on there and ignore what the screen does for now. I'll fix the settings here in a minute. Okay. There's your capacitive reading. You're getting a phase shift on it, which is causing it to draw a circle. Now the neat thing about this is, if you know the source resistance and you know the frequency, you can calculate capacitance. And you calculate capacitance by figuring out where the perfect 90-degree phase shift is. How do you know where the perfect 90-degree phase shift is? You'll get a perfect circle up here, which is why I got the grid. So, capacitance passes AC, blocks DC. So the higher the frequency, the more the capacitor acts like a short. Therefore, when I crank up this frequency a little bit, the circle should get taller and skinnier rather than shorter and fatter. So there you go, see that? It's already at 1800 hertz, 1848 hertz, and it's a pretty good tall signature there. Now I'm going to dial this down until I get to a perfect circle. Until I get to something that looks pretty close to a circle. Now let's let that draw for a minute. Oops, too far. And this might take a little bit. Okay, I'm going out 2 divisions there, just short of 2 divisions, and about 1.5 divisions there. So let's go ahead and raise the frequency a little bit. Okay, I'm 2.2 and 3, a little over 2 3/4 there, a little over 2.5 there. So let's go ahead and raise it a little bit more. Right about there. Draw the grid again. 2 3/4 there. Almost 2 3/4. Go 1 more here. We'll see what happens. 2 3/4. Okay, that looks like about as good of a circle as I need to get. So, capacitive reactance XC goes 1 I'll put this on a piece of paper in front of the camera here in a sec. 1 over 2 pi FC. Capacitive reactance, XC equals 1 over 2 pi FC. We know XC because that's our source resistance. In this case, it's setting number 4, which is 740 ohms. So 740 ohms equals 1 over 2 pi FC. 2 pi F times pi times 223.5 hertz, 1404. Yeah, we'll just go 1404.3 C. So 740 equals 1 over 1404.3 C. 1404.3 C. Multiply by 740 to get the factor over the other side there. Invert it. Figure out how many microfarads it is. 1, 2, 3, 1, 2, 3. 0.96 microfarads is what I calculate. 0.96 microfarads. And if I look at this capacitor, it says 105K on it. 105K is a 1 microfarad capacitor, so it was only 0.04 microfarads off. Where's that 0.04 coming from? It's coming from the fact that I can't zoom in the circle and see if it's a perfect circle or not. But, you know, let's do the math there. 1 divided by 0.96. Yeah, 4% off. Not bad for eyeballing something. So, there you go. That's the basics. Works for me. 17 minutes. Anyways. All this stuff over here is just test. Well, most of this stuff over here is testing stuff. Oh, here we go. I can clear this. I got a deal on here called auto clean. What that does is it tries to get rid of any extraneous points. So let me shut off the continuous scan, clear the screen. I'm going to turn on auto clean, and I'm going to put that capacitor back in there because that's a good way to demonstrate it. Now I'm going to leave auto clean on there for a minute, or off. Now I'm going to go ahead and continue a scan. Count my points here. 260, 300, 400, 500. Yep, there's 500. Okay. Shut that off. Now you can see that's, you know what, maybe I should time this. I'll give it 10 seconds or 5 seconds. Well, 1, 2, 3, 4, 5. I got 280 points, but see there's a lot of, well, not a lot, but there's a bunch of extraneous points here. So I'm going to hit auto clean, and what that's going to do is it's going to cycle through, and it's going to remove any points that don't have neighbors, if you will. It's the best way I can think of it. All right, so that's gone through and wiped once. Now I got 186 points. Great. So I just turn that on and auto clean it a little bit, and it'll just, like I say, if there's anything, maybe I touched something or whatnot and induced a voltage somewhere, and it caused this point here to go on, or that one, or that one, or that one, or that one over there. This will just kind of go through and kind of wipe everything a little bit. And this circle has 845 good points. Okay, so let's stop auto clean and stop scanning that. I can save a snapshot here. Test cap. .pvw or test cap .pocasa wave. Now I'll go ahead and clear the screen. There's no points to be drawn. I'm going to go ahead and draw the grid. Now I'm going to load that test cap. Here's my test cap. Now, just for the sake of argument, I'm going to go ahead and change the frequency a little bit. There. Now I'm going to plug in a simulated second system with a different capacitor in there, a different circuit board, but it's supposedly the same capacitor. And I'm going to rerun my scan. And look at that, there's something different going on here. So I know that what I had before is different to what I've got now. Or maybe I better stop here. Okay, I stop. Maybe I built something up and let me clear the screen. Okay, that's what I had. And now I'm going over to my second board, which I know is, or that's what my good circuit should look like that's on the screen right now. And I go over to my second board and I hit scan. Oh, what the hell's this? Red is what I had and black is what I got. So I had a capacitor and now I've got a diode. What the hell's going on here? And again, there's all kinds of combinations. If you put a capacitor in parallel, well, let me clear the screen here. I'm just going to go ahead and kind of shove that in there a little bit. I better put that back up to 60 hertz so I got a good starting point. It's kind of tough. I should have put this all on a circuit board, a breadboard or something. Damn it. Okay. Here, close enough. Let me clear the screen once more. And this ain't making very good contact, of course. Makes me look like more of an idiot than I already am. Okay. Let's just say that's my good circuit, okay? just pretend that's my good circuit. That's a diode. You can tell by the tail with a capacitor on it. Now let's go ahead and blow out the diode. Well, no. It'd be easier to blow out the capacitor and just leave the diode. So I'm going to save this as, let's just save that as test 1, POCASA wave. No, okay, well, then we'll just save it as test 2, POCASA wave. Let's go ahead and shut everything down here. Now that was capacitor with the diode. Now I'm going to go over to the board that I just checked. Pretend anyways. Now let's load that test 2. That's what I want to have. And what do I got? I got a capacitor over in this region, in the plus region. And over here where the diode starts to turn on, I've still got a capacitor. I don't have a diode anymore, so that tells me that whatever diode is in that circuit is blown out. It's not there anymore. It's not modifying this. And this is interesting. I never noticed that it does that exactly like that. Maybe we throw a resistor in parallel with all this, or maybe we don't. Yeah, close enough. I think you can see the picture there. Makes that little slanted capacitor there. It tells you got a resistance in line with it because the capacitor, which is the elliptical looking thing, plus the resistor, good one, dude. Resistor, which is that 45-degree angle, do the math, and that's what you'll get. You get you that little ellipse across the side there. Blah, 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 right? It works. That's all I can say about that. Down here I got a pulse generator. If you're ever shooting a transistor, you can put your, or let's just go with a MOSFET. If you're ever shooting a MOSFET, you can put your drain and your source across the 2 probes there. And I got a pulse generator output that you can set using these down here, and your gain and your offset for your output for triggering your gate. And you can watch it maybe when it's totally off, which is what's going to happen. If your gate is at 0 volts, you're going to get a flat line there. When you turn your gate on, you throw a couple of volts on or whatnot, it's going to go up and down. And if you just happen to pulse it in the linear region, you'll get somewhere in the middle there if you're not saturated. And same thing goes with the transistor. Let me think, what else? Anything else? I haven't I haven't found a use for the using the triangle wave output. The hell, let's just try it right now. See what the capacitor looks like. Oh yeah, yeah, you'll square it off. Yeah, sure enough, squares it off versus leaving it nice and round. And if you throw a square wave at it, well, that didn't do any good now, does it? Did it just lock up on me? It just locked up on me. No, never mind. I'm not going to do all that. Yeah, I can update the flash remotely, or remotely. I can update the flash with it plugged in and not lose any of the settings. Here I got the channel switches off. I got two 8-pin rows there, 16 channels to work with. I can put the DDS, the ground, on any one of the 16 channels. Put the pulse generator on any one of the channels. If I want to put it right back on the DDS channel, I can. That's about it. And I am out of here.